you're listening to this right now, maybe wearing headphones or, driving in your car, and my voice probably sounds like I'm sitting right next to you.
Yeah, it feels entirely natural.
Right, it feels natural. We don't really question it at all. But the reality is, what you are hearing in this recording or in any modern music, movie, or podcast is a heavily manufactured illusion.
Oh, absolutely.
You are listening to a sculpted version of reality. Welcome to the Deep Dive. Today, we're pulling back the curtain on the invisible tools that shape literally everything we hear, which are audio filters.
And it's one of those things where once you know what to listen for, you can really never unhear it. I mean, you start noticing the architecture of the sound around you
Yeah.
everywhere.
Yeah, it completely ruins watching movies for you. But I've been digging through a fantastic stack of sources for us to tackle this today.
Awesome.
Mostly masterclass tutorials from audio engineering channels like Audio University, Mike Teaches Audacity, MediaTek Institute, and Mixed Signals.
Those are great sources.
They really are. And our mission today is to act as a shortcut to understanding the real mechanics of these filters. We're looking specifically at how things like cutoff frequencies, filter slopes, and resonance impact the overall audio signal processing.
Right, and how that technical stuff actually translates to the media you consume every day.
Exactly. Okay, let's unpack this, because I always assumed fixing audio just meant, turning the volume up or down on different tracks.
A lot of people think that.
Right. But looking at these sources, it is so much more surgical than that.
Well, it has to be surgical. I mean, if you just turn the volume down on a muddy track, it's still muddy,
It's just quieter mud.
Exactly, it's just quieter. Filters allow you to actually reach inside the sound and remove the specific frequencies that are causing the problem. But before we get into the mechanics of how we manipulate that sound, we do need to confront the terminology.
Oh man, the terminology.
Because if you open up any audio software right now, the names of these tools are going to seem entirely backwards.
I actually found it incredibly frustrating when I first started reading through the mixed signal source. It feels deliberately obtuse, honestly.
Really, it does.
When you tell a normal person about a filter, our brain instantly goes to a coffee filter. And the entire point of a coffee filter is to catch the coffee grounds.
Right. It removes the thing it's named after.
Exactly. So logic dictates that an audio tool called a high-pass filter should filter out the high frequencies. But it doesn't.
It does not. And that's because engineers didn't name these tools using a consumer mindset. The analogy provided by the MediaTek Institute source actually reframes this perfectly.
The oil filter one, right?
Yeah. Instead of coffee filter, think of the oil filter in your car.
Right, because the oil filter doesn't remove the oil.
Precisely. It lets the oil pass through freely while the mesh catches the metal shavings and, the junk.
So it's named for what goes through.
Yes. In audio engineering, filters are named for what they allow to survive, not for what they destroy. So when you apply a high-pass filter, you are telling the software to let the high frequencies pass through safely.
And the junk it catches and reduces is the low-frequency bass.
Exactly.
It's an important distinction, even if it's super annoying to unlearn. A high-pass filter, which you'll sometimes see labeled as a low cut, passes the highs and cuts the lows.
Right, they mean the exact same thing.
And a low-pass filter, or high cut, does the exact opposite. It passes the deep lows and cuts out the treble.
Yeah. And in the literature, the frequencies that survive are known as the pass band.
The pass band.
And the frequencies that get chopped off are the stop band.
Which is a very clean way to visualize the two main tools, I think. But you aren't just limited to the top and bottom of the spectrum, right?
Yeah.
You can combine them to get much more specific.
You can. And this is where we get into the bandpass filter.
Which the sources describe as basically squishing a high-pass and a low-pass filter together over the exact same spot.
Yeah, you end up chopping off the extreme lows and the extreme highs, and you're leaving only a narrow little band of frequencies in the middle that are allowed to pass through.
So you just get the middle.
Right. And if you invert that process, you get a band stop filter or a band rejection filter.
So in that one, you let the highs and lows pass normally, but you aggressively scoop out a specific chunk right in the middle.
Exactly. And the Mixed Signals tutorial noted that when you make a bandstop filter extremely narrow and extremely deep, it's referred to as a notch filter.
A notch filter?
Yeah, it's essentially a surgical strike. You use it to remove one very specific, super annoying frequency.
Like the hum of a refrigerator or something.
Exactly like that, without touching the rest of the audio around it.
Okay, so we have 4 basic shapes. High pass, low pass, band pass, and band stop. We know what is passing through. But what I found really eliminating was the explanation of how the filter actually makes these cuts.
Oh, the slopes.
Yeah, because it's not just a brick wall, which is what I pictured.
No. And that is where a lot of people make their first big mistake when trying to clean up audio.
They just chop it.
Yeah, they assume they could just build a wall and delete a sound perfectly.
I was trying to visualize this while reading through the Audio University material. Tell me if this analogy holds up, all right?
Let's hear it.
Let's say you're using a filter to cut out some rumble. You have to set a cutoff frequency, and that cutoff frequency acts like a doorway.
Okay, a doorway.
It's the specific point where the filter officially begins its work. Everything on one side of the doorway is safe. That's the passband.
I like the doorway concept. It clearly marks the boundary.
Right.
But the thing is, as soon as you step through that doorway into the stop band, the audio doesn't just instantly vanish.
Because it's impossible, right?
Right. Infinite attenuation, which would mean the volume drops to absolute zero, the literal millisecond you cross the threshold, is a physical impossibility in these circuits.
So if the cutoff frequency is the doorway, the sound has to decrease gradually as you walk past it. Meaning, every filter essentially has a ramp leading down from that doorway, and the steepness of that ramp is controlled by a setting called the slope.
That's a great way to picture it, yeah. The slope determines the rate of the attenuation. You can choose a very gentle ramp where the volume fades out slowly over a wide range of frequencies.
Or you can choose a slope that is practically a cliff.
Yes, and in technical terms, this slope is measured in decibels per octave.
Okay, let's break that down without getting too bogged down in a math textbook, because the core concept is actually pretty intuitive once you understand the terms.
It is, yeah.
For anyone who might not have a background in music theory, an octave is just a doubling or halving of a frequency, right?
Right, like if you hit a middle C on a piano, the next C up on the keyboard is exactly double the frequency of the first one.
Okay, so the slope is simply telling you how many decibels of volume you lose every time the frequency doubles or halves, depending on which direction your filter is facing.
Precisely. And standard filter slopes you'll encounter in plugins are usually 6, 12, or 24 decibels per octave.
So the higher the number, the steeper the ramp.
Yeah.
A 6 decibel slope is a gentle, lazy decline. A 36 decibel slope is a massive drop-off.
Right.
So if I have a low-pass filter, meaning I'm keeping the lows and cutting the highs, and I set my doorway at 2000 hertz with a gentle 6 decibel slope, as I move into the higher frequencies, the sound gradually gets quieter.
It's very gradually.
By the time I double the frequency to 4000 hertz, the volume of that specific frequency will be reduced by exactly 6 decibels.
Exactly. And if you had chosen a 12 decibel slope, the sound at 4000 hertz would be 12 decibels quieter. It's just a faster fade.
But here's where I really wanted to push back on the sources initially.
Oh, really?
Yeah, because if I have a piece of audio with a horrible high-pitched whine that I want to get rid of, why wouldn't I just use the absolute steepest slope available every single time?
I see where you're going.
Like, why even bother with a gentle 6 decibel ramp when I can use a 36 decibel cliff and completely nuke the problem sound?
It's a completely logical question. I mean, it's exactly what most people do when they first get their hands on an equalizer. But the source from Mike Teaches Audacity demonstrates perfectly why that doesn't actually work in practice.
Oh yeah, the voice example?
Right. He took a simple, clean voice recording and applied a massive 36 decibel low-pass slope to it.
I listened to that example and it absolutely destroyed the audio. It sounded like he was talking through a thick mattress.
Because sound isn't just one single frequency. The human voice, or a guitar, or a piano, is made up of a fundamental frequency and a really complex web of harmonics that stretch way up into the higher registers.
Oh, so the texture is up there too.
Exactly. When you create a massive unnatural cliff with a 36 decibel slope, you aren't just removing the noise. You are aggressively hacking off the upper harmonics of the voice itself.
And it introduces phase distortion, right? I read that the steeper the slope, the more the filter essentially mangles the timing of the frequencies right around the cutoff point.
That's totally right. So a filter is always a compromise. You are trying to find the gentlest slope possible that still effectively reduces the unwanted noise, but without butchering the natural timbre of the instrument or the voice you are trying to preserve.
That distinction really shifted my perspective. It made me realize that these tools aren't just industrial vacuums for sucking out bad noise.
Far from it.
They are acoustic sculpting tools. Which brings up an interesting tension I noticed across all these sources.
What's that?
Well, are audio engineers mostly using filters for damage control, like fixing bad recordings, or are they using them to artificially construct a mix?
It's really heavily weighted toward both. But the way they use them in those two scenarios is completely different.
Let's look at the damage control side first, because that's where high-pass filters are the absolute unsung heroes of modern media.
Oh, 100%.
The Audio University source had a fascinating breakdown of this. Every instrument operates within a specific, useful band of frequencies. Take the male speaking voice, for example. The fundamental frequencies of a typical male voice generally don't go any lower than about 80 hertz.
Which means if you were looking at a recording of a guy talking, any audio information sitting at 40 hertz or 50 hertz isn't his voice. It's impossible.
It's environmental garbage.
Yes.
It's the low-frequency hum of the air conditioner in the building or the rumble of a truck driving by outside the window.
Or just the structural vibration of the building itself,
Yeah.
traveling up through the microphone stand.
And because that low-end rumble doesn't contain any useful vocal information, an engineer can engage a high-pass filter, set the cutoff doorway right around 80 hertz, and just aggressively chop all of it away.
Yep. And suddenly, a track that sounded muddy and amateurish sounds incredibly tight and professional.
And you haven't touched a single frequency of the actual voice.
Not one. It's such a universal trick that microphone manufacturers literally build it into their gear.
Wait, really? The physical gear?
Yeah. If you ever look at a professional microphone and see a tiny little switch with a jagged line icon next to it, that's a built-in high-pass filter.
Oh, I've seen that.
Yeah, they often call it a bass roll-off. It stops the rumble before it even hits the recording software.
That makes so much sense. And it's also the primary defense against plosives, right?
Yes, those massive, booming P-pops.
When someone gets way too close to the mic and says a word starting with P or B, and a literal gust of wind hits the microphone diaphragm.
It sounds like a cannon going off in your headphones.
It really does.
Now, the sources warn that the best way to handle plosives is to just back away from the mic or, use a physical pop shield.
Sure, prevent it at the source.
Right. But if the recording is already done and the pops are in the file, a high-pass filter is your only real option.
Because that gust of wind translates electrically as a massive spike of sub-bass frequency energy.
Exactly. Slicing off the bottom of the audio spectrum essentially deflates the pop entirely.
There's a live sound application to this that I found really interesting too, regarding feedback loops.
Oh, live sound is a whole different beast.
We all know that horrible screeching sound when a microphone gets too close to a speaker. But I didn't realize the physics of why certain frequencies feed back first.
This is a great point to bring up. High frequencies are very directional. Think of a laser pointer.
Okay, a laser.
If a speaker is facing the audience, the high frequencies are shooting straight forward. But low frequencies are much less directional. They are omnidirectional.
Meaning they go everywhere.
Right. They spill out of the speaker in a massive sphere, bouncing off the back wall, the floor, the ceiling.
So if a microphone is sitting on a stage behind the main speakers, the first sounds that are going to bleed backward and hit that microphone diaphragm are almost always those low, bassy frequencies.
Yep, and that starts the feedback loop.
So by aggressively high-passing the microphones on a live stage, the sound engineer is essentially removing the fuel for that low-end feedback fire.
Exactly. They can turn the overall volume of the band up significantly higher before the system starts to howl.
That perfectly encapsulates the utility side of filters, your mitigating disasters. But the other side, the acoustic sculpting, is where mixing becomes an art form.
I completely agree.
Because it's about recognizing that a song has a finite amount of sonic real estate.
That's a really good way to put it.
This was the major aha moment for me. MediaTek Institute used the example of an electric guitar and a bass guitar playing together in a rock song.
Classic example.
If you were the guitar player, you probably spent hours dialing in your amplifier so it sounds massive. It's rich, it has a ton of low-end punch, it shakes the room.
Right, and isolated by itself, it sounds incredible.
But a mix is not about how things sound in isolation. When you take that massive bottom-heavy guitar and you try to play it at the exact same time as a bass guitar, you create a sonic traffic jam.
Oh, a huge one. Both instruments are pumping out enormous amounts of energy in the exact same low-frequency band.
And the result isn't a bigger sound, it's just mud.
Yeah, total mud. The bass guitar loses all its definition, and the mix sounds exhausting to listen to.
So the audio engineer has to step in and make a ruthless decision. They apply a high-pass filter to the electric guitar, carving out its low end.
And honestly, if you soloed that guitar track after the filter was applied, the guitars might actually be horrified.
Because it would sound thin and weak compared to the raw amp sound.
Completely.
But the engineer isn't listening in solo. By carving out the bottom of the electric guitar, they have intentionally manufactured an empty space in the low end of the mix.
And the bass guitar slots perfectly into that empty space.
Suddenly, both instruments are clearly audible. They aren't fighting anymore. They fit together like puzzle pieces.
It's so cool. And you really have to consider how counterintuitive that is for a beginner.
Yeah.
You are making a track sound better by intentionally degrading the full spectrum of one of the instruments.
Speaking of things I never realized were happening behind the scenes, this puzzle piece concept actually occurs physically inside your speakers, too.
Ah, yes.
I knew speakers had different sized cones, like a big woofer for the bass and a little tweeter for the treble, but I always assumed the amplifier just magically knew where to send the sound.
Not at all. The amplifier sends the entire full-frequency audio signal from the deepest bass to the highest treble down one single cable right into the back of the speaker cabinet.
And if that full signal hit both cones, it would be a complete disaster.
A very expensive disaster.
Right. So inside the speaker enclosure, there is a piece of hardware called a crossover network. And a crossover is literally just a combination of filters.
Yeah.
It uses a low-pass filter to block the high frequencies, sending only the heavy bass information down to the big woofer.
Right.
And it uses a high-pass filter to block the bass, sending only the crisp highs up to the delicate tweeter.
And this is about way more than just audio clarity. It's about protecting the hardware from physical destruction.
This part blew my mind.
It's intense. The source material points out that a tweeter is a tiny, delicate piece of material designed to vibrate incredibly fast. If you accidentally bypass that high-pass filter and send a massive surge of low-frequency bass energy into a tweeter, it will physically tear itself apart.
It will explode.
Literally explode. The filter is the only thing standing between the music and blown gear.
Okay, so we've looked at filters as industrial vacuums cleaning up AC noise and P-pops. We've looked at them as scalpels puzzle piecing a rock mix together, and as bodyguards protecting tweeters.
A lot of hats for one tool.
Seriously. But all of that is about removing information. The final concept from these masterclasses flips that entirely. Here's where it gets really interesting, and where filters become actual musical instruments.
We're talking about resonance.
Yes, also known as the Q factor.
Yeah.
Up until now, we've pictured our cutoff frequency as a doorway and the slope as a ramp going down. The filter only subtracts volume, but when you introduce resonance to the circuit, it actually adds volume right at the cutoff point.
Exactly. If you stick with the cliff analogy we used earlier, adding resonance is like taking a magnifying glass and hovering it right over the very edge of the cliff.
Right.
The overall frequency spectrum stays flat, but right before the sound drops off into the stop band, it violently spikes upward in volume.
The Mixed Signals tutorial had a brilliant audio demonstration of this. When you crank the resonance up on a filter, it takes whatever sound is passing through it and imparts a very distinct, colorful, almost whistling tone right at the cutoff frequency.
It's a very recognizable sound.
Yeah, it highlights that exact edge.
Right.
And if you are using a really steep slope, like a 24 decibel per octave cut, that resonant whistle becomes incredibly aggressive.
It does. But, you know, a static whistle sitting at one specific frequency isn't particularly useful on its own.
No.
The real breakthrough in electronic music happened when engineers realized you don't have to leave the cutoff doorway in one place.
You can move it.
You can move it.
You can modulate it. If you have a synthesizer playing a chord and you run it through a low-pass filter with the resonance turned up, you can grab the cutoff frequency knob and physically sweep it up and down the frequency spectrum in real time.
And it creates a massive sense of movement and tension.
It is the absolute backbone of dance music and sound design.
Absolutely.
If you've ever been in a club or listened to an electronic track and you hear that classic swoosh sound, you know, where a synthesizer starts out dark and muffled, and over the course of 8 bars, it slowly opens up.
Right, getting brighter and more laser focused.
Until it finally drops.
Right.
That entirely dramatic buildup is nothing more than someone slowly turning the cutoff knob on a low-pass filter with high resonance.
It's fascinating because it perfectly bridges the gap between pure technical engineering and artistic expression.
Yeah.
The exact same mathematical circuit that allows a podcast editor to invisibly remove the rumble of a passing truck is being used by a DJ to create a massive, sweeping, highly visible musical swell.
It's wild.
The only difference is how aggressively you manipulate the controls.
It gives you total authority over the signal. It also explains how you can use a tool meant for cleaning audio to intentionally ruin it for creative effect.
Oh, like the lo-fi stuff.
Yeah, MediaTek showed how you can take a pristine vocal recording, apply a bandpass filter to chop off all the lush lows and crisp highs, and instantly create that tinny lo-fi sound of an old 1940s telephone.
Or a megaphone.
Exactly. Which is really the core takeaway here. Understanding the pass band, the stop band, the slope of the cut, and the magnifying glass of resonance.
Right.
It means you are no longer a passive listener, you are an architect.
I love that.
So let's tie this all together for everyone listening. Next time you are listening to a podcast where the host is clearly sitting in an untreated hotel room, yet their voice sounds unbelievably clean and rich, you'll know exactly what's happening.
Yep.
You'll picture the 80 hertz high-pass filter quietly slicing away the room noise.
And when you hear a perfectly balanced rock mix, you'll know the guitars have been intentionally hollowed out to make room for the bass.
You now know the invisible slopes and cutoffs working behind the scenes of everything you hear.
But, if audio filters are constantly being used by engineers to carve away frequencies, to aggressively roll off the lows, and to meticulously puzzle piece every single element together so that a mix sounds perfect,
Yeah.
it begs a really profound question. How much of the natural, pristine sound in our favorite music and media is actually just a highly sculpted, artificial reality?
Wow.
If everything we hear is filtered to fit, it makes you wonder what the raw, chaotic, unfiltered world actually sounds like.